So our next speaker is Anatol Kirillov. With his talk about quadratic algebras, Schubert calculus, and small quantum cohomology of flag variety in type A.
Thank you for introduction, and I want to thank the organizers for kind help to prepare slides and so on. I want to say about my problem really is a connection between algebraic geometry, representation theory, and the special functions and several different subjects with mathematical physics. Because in mathematical physics there are many very interesting formulas, very interesting ideas, and I wanted to understand what does it mean for classical problems of algebraic geometry and algebraic combinatorics. And the main target of my research is to understand what is structural constant for certain polynomials which appears in algebraic geometry, like Schubert structural constant, Grothendieck structural constant, and many others. I don't know what is it.
Верхненькая вперед, нижненькая назад.
Okay, okay, this is some plan of my talks. I'm not sure that I can take all things, but nevertheless, one of my points is I was really surprised that many computations, for example, in quantum groups and algebraic geometry, is that in the interval system, that varies the interval system of rational, trigonometric, and elliptic, and basically algebraic part of this theory really basically the same. Of course, the difference appears when you consider representation of this object and the problem of diagonalization and so on. And now I want to say a few words about motivation. My main motivation comes, as I said, from algebraic geometry and combinatorics. This is a Schubert calculus, Schubert-Grothendieck calculus, and also Hirzebruch calculus, and some questions related with some polynomials related with classes, cohomology classes, K-theoretic classes in ring of cohomology ring of flag varieties, and so on. This is one point of view, one subject which I want to study using certain ideas. It is partly from representation theory, partly from mathematical physics, and this is so-called very famous and oops, sorry. Yes, the main idea of my computations is the theory of generating functions, because really any discrete object and any discrete sequence of numbers becomes much more clear and understandable if we consider we study generating function of these quantities. And maybe I can show how it looks if we can try to construct generating functions, but non-commutative algebra. And this generating functions becomes not tractable if I consider it as standard generating functions for quantities, and becomes much more understandable if I consider this object generating function in the non-commutative subject. Yes, and I probably forgot here said that another my motivation comes from the very famous and celebrated theorem of Charles Dunkl. This is a theorem about truncated Dunkl operators. Of course, it is well known that in many interval systems, the using Dunkl operators, which differential operators degree 1, it is in some sense more suitable and either the Hamiltonian, which is the differential operators of second order. Yes, and the result of Charles Dunkl that for any finite complex reflection group, we can construct the family of differential operators, now called Dunkl elements, such Dunkl operators which commute. It is invariant with respect to action of a complex reflection group, and less known result of Dunkl that if we consider truncated Dunkl operators, that means we consider the so-called Dunkl element at critical level. So this is some Dunkl expressions which don't contain the differential part. And one of my project is to look on the algebra generated by Dunkl operators at level 0. Yes, and this result valid for any complex reflection group. So we don't know any good geometrical object behind these algebras. And for some special cases, this is so-called Weil group case or Lie algebras, Lie group case, finite dimensional Lie algebras, Lie group case. The corresponding Y group, the coinvariant algebra of the corresponding Y group has nice interpretation as a cohomology of a corresponding Flach variety or parabolic Flach variety. It has a geometric meaning. And my idea was to look on the algebra generated by truncated Dunkl operators as a set of generators in this corresponding Flach variety, because these generators can be interpreted as a certain kind of operators. And I will show it a bit later. And here I just want to say why generating functions for, in this case, Schubert polynomials or Grothendieck polynomials becomes much easier if we consider some algebras, non-commutative algebras, with the so-called Nil-Coxeter algebras and Nil-Hecke algebras. In this case, the difference between these algebras is a square of generators. This is fundamental difference in my context because square of difference operators distinguish different cohomology theorem and quantum cohomology and so on. Probably it will be clear a bit later. Okay, so we see that relation the same, but Uij square is different. One is just nil, 0, another is a projector. This is and this is difference on the language of cohomology theory corresponds to first one. It is cohomology theory. The second one is the beta cohomology, beta K-theory, because classical K-theory corresponds to case beta equal to -1. But in many questions, it is a very interesting specialization of corresponding Quadratic polynomials, for example, 1, 1, 1, 1. But in this case, the classical Quadratic polynomials equal to 1 and don't contain any information about corresponding permutation. But if beta not equal to 1, it gives you certain polynomials, and these polynomials reflect certain parameters of the corresponding Schubert cells and so on. So I just want to stress that beta K-theory is very, in my context, very important. Okay. So this is just, again, this is Charles Dunkl. I just show the Kirillov and Eric Opdam theorem about the coinvariant algebra of complex reflection groups. It is some comments to this connection of this one is with cohomology and K-theory. Now I just want to define the algebra, the main object of my research. And this algebra, some quadratic algebras, and this algebra really, so the set of generators of this algebra corresponds to the root system of corresponding Lie group or Lie algebra, but to be compact, and I want to illustrate the main idea of this construction on the type A, because I a bit later defined what is Dunkl elements, and the Dunkl elements has the explicit formula really for any root systems, and at least for finite dimensional Wile type, for crystallographic case, and for a complex reflection group of type G1n, we can use some induction procedure and prove formulas which I want to state in type A, because for other types it is rather involved and rather technical. Okay, so algebra, it is just a quotient of free associative algebra by, no, this is just free associative algebra generated by a set of generators Uij, and you can look on Ij as on of positive or as a root of type A. This is an analogy with root system that is very important for other cases. Okay, so now I want to define some kind of main object of my talk. This is Dunkl elements. And this is really a generalization of Dunkl, truncated Dunkl elements, because I introduce certain element Zi inside. So this is the Dunkl element, it is Zi plus some elements of our associative algebra, and row of diagonal elements of this algebra and elements corresponding to root, that means I not equal to j, is entirely different, because I take Uij, this is in some representation, it is really connections. In some sense, it corresponds to, this is my opinion, to some fields in the theory, okay, in some theory. And Zi, it is just operators which act on this on our part of generators. And classical integrable system case corresponds to the case that Zi is a differential operator with respect to variables some xi, with respect to some variable xi. In this case, uij should depend on xi, and so on. And truncated Dunkl operators corresponds to the generated Zi, which is tractable as operators of multiplication by variables xi. Later we will see in cohomology ring of flag variety. Yes, but of course instead of the I, we can substitute, for example, shift operators. For example, we can put Heisenberg operators, which means theta j involves differential operators and operators of multiplication by variables xi. And okay, there are several cases when you put when you can treat that I as in different way. But I want to consider the Dunkl case. That means that I is has a special commutation relations with generators UI. So here I wrote a trivial computation. What is commutant? How to compute commutant of these elements. And it's a commutation divisible by 5 cases. I have first case, this is called curvature, zero curvature condition on some connections, because again, in many cases, you can interpret element Zi plus Uij as connection on the configuration space of certain manifold. Yes, and this is even in this case, this relation that curvature is equal to 0, it is a way to construct a lot of integrable systems, including KP type and so on. I don't look on these cases because in flag varieties it is just a homology of P projective one-dimensional projective space, very trivial case from point of view of Schubert calculus, but it is highly non-trivial case. This is, I want to treat this case in direction of generalized cohomology, quantum cohomology, and so on. Yes, and the second case also it's also some condition which common in physics. That means that this Uij should be translated equivariant. That means that Uij as function should depend on difference of variety of variables, because derivatives with respect to I, J, okay. This is also in L, it is also, I put equal to 0. It is another relations on this algebra. The third condition, this is also very famous relations. This is means, this is relations of homogeneity. This is really means that sum of the I is that Uij commute sum of the I. This is in some realization of differential realization. This is Euler operators, and it should commute with Uij. And this is really a very important property in the context of Schubert polynomials. It describes action of Euler operators on the Schubert polynomials. Anyway, so we have such type of relations, And now we have main, okay, not main, one of the relation of Young-Baxter type, but if we add variables, it will be dynamical Young-Baxter equation. And but again, there is some difference. If you can see that in one case, in this case, I consider not ij but ji. This is a difference which shows that there is a difference between unitary case and non-unitary case. If it is unitary, if uij corresponds to unitary case, that means uij is equal uij plus uji is equal to 0. In this case, you can easily to write is a standard Young-Baxter, classical Young-Baxter equation. Yes, and I want to say that one of my ideas to consider not only unitary case, this is standard case in the theory of integrable systems, but non-unitary case, looking on this picture as part of graph theory and finite type invariance theory, and so it will be later. Maybe I will connect it. And I have last relations. This is relations of commutativity. This is a relation. This is locality relations for particles or for something which are have completely different indices. If ij, ij, not different, then we have relations, we have Fomin relations, also very famous relations in the topology and many other things. Yes, and I want to say that this is really relations was, I don't know who first will introduce it, but it was used Yuri Manin, in the construction of algebra functions on the general linear groups. Yes, but he used also another function condition which is different from this one, but it is easy to see that Manin relations, algebra functions on quantum on general linear groups, in the sense of representation theory, that it means which is algebra generated by matrix element of all finite dimensionally reducible representation of GLN is exactly this is a particular case of this algebra, and the additional condition is that uij, that generated uij, uij, uik, they commute. That corresponds to the case that elements in the column of matrix of Manin matrices should commute. Anyway, and one problem is what is algebra dual? What is a group or some I don't some maybe Hopf algebra, which corresponds to this algebra, dual of this algebra in the sense of Faddeev, Rezhetikhin, Takhtat. Yes, this will be, so in some sense I treated this algebra as algebra dual to the generally some object with general linear groups. Okay, so I call this six-term relation algebra because in my approach, various four-term relations or various three-dimensional relations algebra, various two-term relations algebra, which is really interesting in, 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 So I defined this one, and it is easy if I factorize these 6-term relations by relations which is written here. This will be just ring of polynomials of this. Yes. Now I just want to connect with Algebra case with the integrable systems, and I want to say that this is not only one example, and it will be clear later that really most of all integrable system which admits Hamiltonian of which admits representation really sum of squares of Dunkl elements. In this case, you can write these Dunkl elements in the form which is written here, and without specification what is Uij. Different, for example, in Algebra case, it is just what is called divided difference operators. And again, fundamental property of divided difference operators, Uij square equal to 0. And from my point of view, this is cohomology theory. Yes, and I want to say that really integrable case also can be included in this picture, just specification of commutativity relations between Zj, in this case differential operators, and Uij, which is fields, and I will write this relation. This is a really basic difficulties, problem to develop this theory for integrable case, which I skip really, because I want to study algebra generated by truncated Dunkl operators, because this is a very rich subject. Well, so you see the difference between these elements is again expressed involves this element, and some interesting remark that really these operators, if we consider in the context of differential operators, this is really the operators which transform polynomials to polynomials. This is not entirely obvious, but nevertheless. So it's that means that this Hamiltonian, which is sum of squares of operators, is in some sense is перевод, it transform polynomials to polynomials. So we have diagonalization of this action and so. Yes. I just want to say that you can read. Okay, I will skip. Oops. Yes, now I want to define, generalize, free-term relation algebra. This is just axioms which I mentioned before. So we have so-called locality principle. This is really standard conjectures in the classical physics. This goes back to Einstein, that all particles should commute if we locate it on different positions, and this is so-called factorizability, that all actions between particles appears only for systems rank 2, and this is important for generalization of theory. So for any subsystem of 2, we construct certain relations, and these relations written here. This is again very important remark that any solutions to quantum Young-Baxter equations. This is this is relations of degree 3 really appears as consequence of so-called associative Young-Baxter equation, and I will give a sample of this. And for example, famous solutions to Below-Drinfeld, elliptic solution to Below-Drinfeld, and many very degeneration of this solution, in fact, satisfy associative Young-Baxter equation, which is a free-term relation, quadratic free-term relation, and by this reason I call the quotient of six-term relations by these relations as a quadratic algebra. So this is quadratic algebra, but this is non-commutative case, so we have two relations, and one very important, at least for me, case, unitarity, because standard unitarity is just uij plus ugi is equal to 0, but all the formulas works, okay, but algebraic approach says that unitary case, this is K-theoretic case, when beta not equal to 0. And I also should add so-called exchange relations, how variables that I commute with fields uij, and the relation looks very simple. It's really, how to say, image of Heisenberg relations in this two-dimensional case. So this sum is equal to D, where D is a parameter, that means it's a central element of this algebra. And I want to stress that if D equal to 0, this is a case of Hecke algebra case, but if you D equal to 1, this is Grothendieck case, and I call the polynomials which appears from this in this algebra. It is Hecke-Grothendieck polynomials. This is in some sense very, in some sense, useful union of Grothendieck and Hecke polynomials. Anyway, and now I want to I want to talk about the main relations in this story, the main relation in quantization, but not big quantization, but small quantization. And I just want to say that what I did, I construct big enough commutative, non-commutative algebra, and also big enough commutative subalgebra, and I consider big algebra as quantization of commutative subalgebra, and this quantization depends on the relations in this algebra. We consider, and again, I want to say, it depends what square of generators of this algebra. This depends what is square, for example, solutions due to Drinfeld and Below-Drinfeld, and condition is the following: that uij square should be proportional, should be okay, uij square minus beta uij it is equal to qij, and the cases which I consider, I suppose that qij is a quasi-constant. That means it is either commute with our algebra, or it corresponds to reflection operators. It acts on the uij as a reflection operator. Okay, and again, I want to stress that this is the element Qij. In general, it is parameters of quantization of Schubert polynomials, and this is a small quantization of cohomology ring over the Flach varieties and varieties close to these Flach varieties, like parabolic Flach varieties, Hessenberg varieties, and so on. And again, in these relations, it will be clear a bit later, important things that elliptic case, which I suppose explain a bit later, this is Qij, it is not central, it is not constant, but it is quasi-constant. Okay. Oops. Yes, now I want to look to show what is difference between what abstraction appears in the quantum Young-Baxter equation in the in quantized case. Of course, quantum term quantum used in many contexts, and in this case it is not quantum in the sense of quantum Lie algebras. It is a quantum in the sense of quantum deformation of structural constant in intersection index geometrical intersection index of certain cycles. This is deformation of structural constant, multiplication of Schubert or Grothendieck or related problem. Okay, so you see that quantum Young-Baxter relations has additional term which is commutator with Qij, and if Qij is constant, this is zero, so we have honest Young-Baxter equations. But in the case of Coxeter relations, I also one of assumptions is that Qij is central element. It is shows that Coxeter relations is just multiplication of Qij. Where it is? Sorry. 5 minutes? Okay, I will skip this one thing, and I will, there is a lot of...
У вас 10 минут?
10 minutes?
Да.
Okay, thanks. Well, what I skip? Anyway, okay, this is some example of Dunkl elements. This is a sample of Dunkl elements, and I consider a non-unitary case. That means here, okay, I just want to, anyway, my main result is that for this, okay, this is not exactly, this is a result of Fomin and myself, and it was generalized by myself and Maeno, and generalized by myself in multiplicative case. Okay, so this is really quantization of elementary symmetric polynomials in this algebra. That means in this algebra, any elementary value or any quantization of elementary symmetric functions can be written in this form. Really, what is written here? It is written here, value of elementary symmetric function on Dunkl elements. And this is main things which I want to ask audience, because in this context, as I showed, the definition of polynomials really need only one variable case. Well, okay, so this is, I just So this is there is a very interesting case of affine algebra. This is in this case algebra also finite dimensional and very interesting. Okay, this is I skip. This is I skip. This is I skip. This is I skip. Okay. Anyway, I want to. Yeah, I understand. I just want to. Well, anyway, now I just want to say what is a multiplicative theory. So, as I told, it was additive Dunkl operators and additive Dunkl, truncated Dunkl operators. Now I want to say that this algebra really contains multiplicative case, because really K-theory has two variants, one additive and another multiplicative, and the multiplicative case based on this algebra and on some relations, which is really relation for so-called affine 3D and algebra, which was studied by myself and Maeno. Okay. Okay, so what is definition of multiplicative Dunkl operators? This is really generalization of Rusinar's McDonald polynomials, because in some special case you obtain Rusinar's multiplicative. Okay, I skip Rusinar-Schneider case, which corresponds to additive case, but multiplicative case corresponds to Rusinar's McDonald polynomials. Anyway, we have, it is really a result, so I defined these operators. Really it is almost the same as, this is multiplicative form of truncated Dunkl operators. So they commute. This is a result really which goes back to the Young, the same Young as Young-Baxter equations, and also to Jung, which is another famous person who described representation theory of symmetric group and general linear group and so on. Okay, so, and consequence that this HIA function satisfy the what I called constant Young-Baxter equation. And this is just some more or less simple case of using Young-Baxter equations. Okay, and so one of my results is computer description of algebra generated by multiplicative Dunkl elements. Yes, and I just wanted to elliptic case. What is elliptic case? Now, elliptic case based on the theory of elliptic function, and I just mentioned here briefly what is. I don't write explicit definition of elliptic function because it was mentioned many times. Yes, and now I consider what is known as Kronecker sigma functions. Really, this function appears, you can see this function in exercises to the book Whittaker and Watson, now it's more than 100 years ago. And this function appears later very often in basically in all papers on integrable systems. Yeah, yes, because this function has a natural generalization on Riemann theta functions, which I also have to skip. And okay, so now this is also a very famous result of Hermite, which is maybe 200 years ago, that this function satisfy free-term relations. But again, up with some changes, in order to have a correct free-time associative Young-Baxter equation, we have to multiply this elliptic function on the exchange operators, and we have an honest functions. Yes, and so I will write relations on this case, and the square of this element should be difference of two P-Weierstrass functions. One function difference of variables, and another one difference of variables. And because we remember that in quantum case, the honest Young-Baxter quantum Young-Baxter equation not equal to 0. Now we have to quantize this element, and this can be quantized very some simple ways, because I mentioned that hix will be 1 plus x uij. In this case, we have we need to introduce new parameters, new variable, new variable Cij, and consider operator Rij. This is and yes, and this is exactly exercise using freedom relations for Uij and modified free to relations for Uij and relations for Uij square. We have here Uij square is equal to difference is equal to sigma function. Yes. And now I just want to introduce new parameter. Really, this is an operator. I need to introduce a certain set of new generators Li, such that okay, there is some misprint. Okay. Okay, Lj multiplied by Rij is equal. Okay, this is a relation written in opposite. Rij Li is equal to Rj. Yes, this is and this relation allows to put Li in the Dunkl multiplicative Dunkl element, and in the case when Li is shift operators. When, again, as I mentioned, you need translation invariance, these operators commute. Yes, and you can plug instead of Li really operator multiplication by Xi and identity operators or shift operators. You still keep commutativity of your Young-Baxter equations. And one important thing is really that Rij in this case, this is not, this is really a family of operators, because Cij, which I mentioned, really depends on certain parameters. So we obtain certain parametric solutions to the Young-Baxter, elliptic Young-Baxter equations, and so on. But point there are no direct connections here with elliptic Hecke algebra, because on this case you can easily, okay, using these operators you can construct elliptic representation of symmetric group. Yes, this is important. Okay, this is also interesting stuff. Yes, and really my result is that you, in the case when Li, these operators, is, I write here for simplicity the case that it is identical operators. Again, you can compute, you can construct interval of motion of these connections. That means these operators, value of these operators on Dunkl elements does not depend on variables Uij or the field. So this is integrable of motion, And really, I computed explicitly this integral of motion in elliptic case, and this is a bit difference because you have in elliptic case you have additional term in degree 4, which is consists of product of Weierstrass functions. So you obtain a new quantum quasi, but this is constant because with some really commute with Dunkl operators. Okay, so and I will skip case higher genus. So, thank you very much.
Okay. So thank you, Anatoly, for his nice talk. Questions?
Toля, but you need parameters. You have formal algebraic theory, but to obtain a Frankl-Shetikhin quantum KZ elliptic, for instance, right? You need parameters, differences of parameters, something like this. Where are the parameters?
Again, as I mentioned, I consider the case where we don't have differential operators. And this formula, parameters, there are a lot of parameters.
Xi minus xj, well, x1 minus x2, anyway, some kind of standard parameters
this is algebraic, how to say, this is depends on representation. If I take representation, for example, Gaden representation, that means Uij it is divided difference operators. Additional parameter you have choosing the K-theory. This is Uij really contains this is quantum. It contains a lot of parameters. It contains quantum parameters. It contains K-theoretical parameters. It contains parameter D. Many, but again, I don't. Again, this is a case, truncated case. That means I consider, if you wish, truncated KZ equation.
I understand, but you see, actually it is two-stage construction. First, we begin with quantum KZ, then we consider monodromy, and monodromy will produce Dunkl operators. You need something else. You need to consider some kind of
monodromy. Right? I think also gives you.
Otherwise, it looks like quantum KZ, Frankl-Shetikhin system, right?
But I don't say anything. I can define quantum KZ, but again, this is operators which contain differential part of shift part. But Dunkl, truncated Dunkl operators, it is just operators which don't contain either differential or either shift type.
Okay.
And if you want to include differential part, you have to study not Flach varieties, but tangent space for Flach varieties. In this is another story.
Other questions?
So in the title, there was a small quantum cohomology.
So this is small quantum cohomology.
Yes. So can you show the slide when you explain why this is small quantum cohomology?
Sure.
Which object is defined as corresponding ring or whatever?
Again, this is really small quantum cohomology if I consider limit t of a parameter to 0. This is deformation. Okay, anyway, I will try to find it. Yeah, well, I skip a really very important connection with algebraic geometry. We have classes of Schubert cells, and this is main idea of generating functions for value of Dunkl operators on the value of Schubert polynomials on Dunkl operators really is generating functions in representation, gives you generating functions for Schubert structural constant for so-called Goretsky Chern-Schwarz McPherson classes, for Severi classes, for many classes, for Peterson classes. Anyway, this is basic idea that this is basic idea that value of, for example, of Macdonald polynomials on this multiplicative Dunkl operators, it's also count the structural constant in something described Pierre rule. Okay, where cohomology? Yes, this is cohomology. A statement that ring of Z is generated by additive Dunkl operators isomorphic to cohomology ring of Lac varieties. And if I say that this is written in the case that all coefficients, I think this is for Fomin Kirillov algebra, the case that you don't have quantization, but quantization means that value of Dunkl, value of ring of in fact it's not Z of Dunkl elements isomorphic to cohomology ring of quantum cohomology of Lac variety. That means that quantum elementary symmetric function generate the cohomology ring or quantum cohomology ring for Lac variety. That means that multiplication, that we have a deformation of multiplication of Schubert polynomials in this algebra. I think I wrote somewhere, but I don't see. But anyway, this is anyway, the theorem is that Dunkl operators after modification, Dunkl operators the same, no changes. But algebra generated by Dunkl elements, it is standard cohomology plus deformation of this cohomology, which comes from deformation of relations. This is the point that algebra deformation corresponds to deformation of algebra. This is really what on example of Lie algebras when we in the talk of Ettinghoff that he wants to quantize Poisson brackets, and he can consider it as a multiplication. Okay, I will stop.
Let's thank you, Professor Kirillov.